And we will proceed. We will start with the first plenary session, number 1. During this plenary session number 1, we have opportunity to listen 3 key eminent speakers from different countries. I will chair this session, and Ms. Amparo Gonzalez from International Atomic Energy Agency will help me with co-chairing. Let me introduce you 3 of our speakers. Dr. Evgeny Adamov will make presentation from Russian Federation. Dr. Yu Hong will make presentation from China. And Mr. Sylvestre Pivet will make presentation from France. And now, we are ready to start our plenary session number 1. And listen presentation from Evgeny Adamov. But before we start, I will introduce more detail. Evgeny Adamov was Russian Minister of Atomic Energy in 1998-2001. Dr. Adamov was educated in various Russian nuclear facilities with an emphasis on the space applications of nuclear technology. He did follow up postgraduate work at the Kurchatov Institute with specialization on liquid metal coolants and control systems. Following the Chernobyl accident, Dr. Adamov was heavily involved in mitigation and cleanup activities, and at that point became director of the Research and Development Institute of Power Engineering, leading the effort to modify and upgrade RBMK reactors with the aim of raising their operations to a safety level comparable to that of Western reactors of the same vintage. Professor Adamov has spent more than 25 years guiding the development of innovative nuclear reactors and their fuel cycle, with the goal of reducing radioactive waste while increasing safety and proliferation resistance. He is the author of several monograms and more than 300 publications and inventions, the recipient of numerous awards and honors, and a member of several Russian scientific societies. Please, Dr. Adamov, floor is yours.
Thank you very much. Good morning, ladies and gentlemen. It's a very unusual situation that my bad English will be a language for presentation, and many people who better understand Russian will receive this information as interpreter. But I check what happens in the opening session. We have very good interpreter, and I hope that you receive good information. Well, let us go. Wait a moment. Хочу поставить все. Я не вижу мышки. this technical problem cannot be resolved on my computer. But in any case, you see my presentation in these monitors, and what I do in the computer doesn't help. Okay. Now you see what is the main goals of project PRORIC. Because it's announcements more than 10 years, I'm not on a position. No, it doesn't announcement. Он не был провозглашен 10 лет назад, он был провозглашен 5 лет назад. But the goals of this project really known more than 10 years. And only one remark. You see, 10 years ago, we think that economic was its last position. Now, it's quite different situation. And all other goals is after economic. What we do now is not only discussion in conference. You know that in our country there are great events. We have now in operation not only BN 600, but at the same time BN 800 working. And in the place of Siberian chemical, Сибирском химическом комбинате, we began construction, pilot project, which include all the phase of closed fuel cycle. On this picture, you see 3 stages. In first stage, so you see in first stage, we create a fabric for production, a new fuel. It's ну ладно, we have quite different presentation. You see, type of fuel, it's mixed nitride, uranium, plutonium fuel. It's more density than oxide, and give for us some advantage. Main parameters of pilot reactor you can see here. Here I can show you how it's developed situation in the construction in autumn last year and spring this year. It's also show that it's great progress, and we hope that we have possibility to begin production of fuel in 2020. Now I can show you what this type of fuel, what advantages it gives for us if we compare with oxide. Please see this picture. I try to find. No, it's better if you upper part of the picture. It's parameters for BN 1200. But if we use oxide, we have high reactivity, near the same as we have in BN 800. If we use this fuel, high density fuel, we have possibility to completely exclude such reactivity excursion, reactivnostные аварии, and completely exclude such accident as we have in Chernobyl. And another problem, we know that we have in the history of atomic energy, we have 6 great accidents. Most of them connected with loss of fuelant. Loss of fuelant and loss of coolant of core. Here in the picture exists the design of BN 1200. It's completely integrated, and it's not possible to lose coolant from this design. So, 2 main accidents, reactivity and loss of coolant, completely exclude design and physical methods. And last figure which exists in this, not figure but рисунок, thank you. It shows how we resolve the problem of spent fuel. Fast breeder reactors give for us possibility to burn actinoids and receive equilibrium, равенство, between waste and raw materials, сырье и сырье, in the period between 100 or 500 years. It depends how we prepare raw отходы. And if we take into account migration factor, it's less than 500. But if we don't take into account, it's around 500 years. 500 лет, 500. Спасибо. There are very interesting report here about coolant. I don't in a position to read all of this chart. I think that's very important. That's what we have possibility with this coolant. We increase the natural circulation and decrease the loss of pressure. As an advantage you also see in this picture. Absence of VIP smooth. In open session, there are, today in the open session, there are information that there are two type of reactors, or maybe with heavy metals reactors, with lead or with lead bismuth. From very beginning, I want to say that it's not very important sodium, lead or lead bismuth. It's important that all 6 goals which exist in previous slides are fulfilled in the project. This presentation is exists in the files, so you can check that with this type of coolant, with this type of fuel, you have very good safety parameters which exclude evacuation of people in as in very severe accident. But the probability of such accident is also very low. Please check it in last sentence in this picture. I say about radiation equivalent management, достижение радиоэквивалентности. But please take into account that it's only in such case if you return from the East not only uranium, вы добываете, если вы добываете not only uranium, but in the same time radium and thorium. In such case, it's possible to have radiation equivalent management. This show for you where we perform main experiments with this type of fuel. Now, best what we have is 7.4% burn up. All assemblies which we excavate from core, it's maintain integrity, сохранили герметичность. And several of them are go through post-reactor examination. There are several reports. In this conference, you receive several reports which give details of such experiments, and I have possibility don't stop on this. All of people, as I understand, well known what is the design and what is the advantage of BN 1200. Now, as Mr. Peshukov say, there are process of expertise of this project, and I very hope, I think I hope that it will be economically have an economic advantage with VVER reactors. First of all, for us, VVER reactors. In such case, it has possibility to create it. Here you have information about new generation codes. Some of them justified and some of them receive permission from regulator. But for all of them, we wait this in the end of this period, 2020. It doesn't mean that we finish the working in this year, but what we do now, we think that we finish in this period. And maybe it's most important the problem of economic. Here we see our criteria, which is applied not only for fast reactors, but also for thermal reactors. Unfortunately now, even in our country, they are not comparable with steam gas installations. And our criteria show that we have advantage not only with VVER, but with steam gas installation, if we will succeed in design and building such reactors. In any case, in nearest period, this century, we wait two-component nuclear power. And you see that if we try to do, if we continue only what we do today, in end of this century, we completely lost nuclear in our country. And only if we develop closed fuel cycle and fast reactors, it will be developed and realize all the advantage of nuclear energy. There are three main conclusions. First, we not only have practice with existing sodium-cooled reactors, but in parallel, we develop reactors with heavy metals, and a pilot project now is developed near the Tomsk. In 5 years in 5 years of the realization of this past течение, we think that we show advantage of closed fuel cycle and fast reactors to resolve all the goals from which I began my presentation. Thank you very much.
Thank you very much, Dr. Adamov, for your nice detailed presentations. And we have time for the several couple questions from audience. Please ask questions. Do we have questions?
Somebody wake up, auditorium.
My name is Shigenobu Kubo, JEA Japan. I have a question about the comparison between sodium and lead or lead bismuth. You mentioned it doesn't matter as far as it's clear the criteria. But I think the power level is very different from BN1200 and breast 300. So this difference means the economic competitiveness is different. So how do you think about this point? And now you are going to develop these two types of reactors, but when or how to decide which one is better, or you should keep these two types of reactors to develop even in the future and commercialization era?
Thank you very much for your question. I'm especially, when you raise your question, open this picture. And you can check that all the goals we can resolve with all types reactors, with all types of columns. But with heavy metals, we haven't such problems which fire, explosions, which exist when we use sodium. With lead or heavy metals, pins will have a big distance between pins, and we have possibility to decrease loss of pressure and receive a better natural circulation. And there are no big difference between lead and lead bismuth. Of course, if we use eutectic natrium and sodium, natric kali, in such case we have melt temperature, is room melt temperature. But if you use bismuth, lead bismuth, and lead, there are differences between them. But in all the cases, we need to heat the tubes to prevent замерзание, frozen. And with bismuth, we have problem with polonium. And last, the ability bismuth in the E-scale, земной коре, it's not the same as lead. As a result, the price of bismuth is higher than price of lead. That's all. And next part of your question is why we develop both type. First of all, because we have more experience with lead, with sodium, sorry. And if we can resolve 5 of these goals with sodium, why not? And in future, we can avoid the problem which exists with sodium if we succeed with lead. Thank you.
Thank you, Dr. Adamov. One more question.
Frédéric Serre from CA France. You have shown that by using uranium, plutonium, nitrile fuel, is safer than using oxide fuel. So my question is it easy to start a reactor with MOX fuel and later on, after demonstrating that MNUP fuel is better, to switch from MOX fuel to MNUP fuel in the same nuclear plant without major change of the reactor?
I'm not sure that it's possible. Of course, maybe we find such a way, but you know that reactor breast began very beginning from oxide fuel, from nitride fuel. But BN 1200 maybe began with MOX, and in such case receive such problem as you say. But my personal position we have enough time for any predicted period to begin working with BN 1200. No, in any case, it's no early, not early than 2025. In such case, if we have now 7.4% burn-up, we have possibility to increase this figure, as I hope, and receive between 10 and 12. In such case, it's possible to resolve all the advantage as I show in this picture with the reactivity margin. Thank you.
Thank you very much, Dr. Adamov. And I think that at the end, if we have time, we can continue with questions to all key speakers. And thanks, and let's applaud again to Dr. Adamov. Thanks again for nice presentation. I hope in several years we could see both BN 1200 and the breast also, and to compare that different ways with different coolants. Okay, our second eminent speaker, Dr. Hong Yu from China. And he will present that research development and fast reactors and related fuel cycle in China. Dr. Yu engaged in fast reactor and related fuel cycle development strategy and study, and fast reactor neutronics, safety analysis, and he was responsible for co-design and physical startup of a Chinese fast reactor. Please, Dr. Yu, the floor is yours.
Thanks for the chairman and ladies and gentlemen. It's my great honor to make the keynote speech. So it's great honor for me to make this presentation on behalf of the Dr. Zhang Donghui. Yeah, my name, my title of the paper is the research, development, and deployment of the fast reactor related fuel cycle in China. Include the 4 parts. The first, I will give you the general information of the nuclear power plant in China, and then I will introduce the sodium fast reactors in China, include the CFR in operation, and another fast reactor is FR17 in design, and then some information about the fuel cycle, the closed fuel cycle consideration in China. As you know, in the last year, in 2016, the China perimeter energy consumption is a little decreased, and so you can see the potential of many kind of energies in China, include the crude oil, the natural gas, and the long-core electrical consumption amount, yes. And in the last year, the government also issued the nuclear power development the policy. In 2020, the amount of the nuclear power plant will reach 50 gigawatts in operation, and the 38 gigawatts in construction. So totally is the 88 gigawatts for nuclear power in China by 2020. And so there's some studies from the institutes show that by 2030, the total number of the nuclear power will reach 200 gigawatts. And in the middle of our century, the amount of the nuclear power will reach 400 or 500 gigawatts in China. Now, nuclear power plant unit in operation is 35, and another 19 units in construction in the end of last year. Also, we can show some, the nuclear power plants operation reports in last year. In last year, China's electricity industry generated a total of 591 trillion kilowatt hours, and included more than 200 billion kilowatt hours of nuclear power. And the nuclear energy grows more than 20% from 2015. So the average utilization of the nuclear power plant in China has declined in last 3 years. For the China economic is in a period of adjustment, and so the coal price is fell down, and so the watt abundant and hydroelectric increased. So the operation of the nuclear plants in China kept safe. There's no Alice level 2. Yeah. In this case, I think the PWR or the the larger size nuclear power plant and the continuous development is the base of for the fast reactor development. Yeah. So the second part is the sodium fast reactor. We in the last year our government issued the nuclear power energy development policy, focus on the safety and the high efficiency. And so we keep the the development strategy in 3 steps. The first step is the thermal reactor, and the second is the fast reactor, and the third is the fusion in the future. Now, and maybe in the next 10 years or more long, the PWR is the main type of the thermal reactor in China. And we also said that the closed field cycle will be developed with the nuclear power stations at the same time. So the task of the fast reactor, I think, we use to support the sustainable development of the nuclear energy, include the raising the utility ratio of the uranium resource, and also include the transmutation of the long-life radioactivity product from the reactors. Concerning with the fast reactor development strategy, in China we can say that the 3 steps. The first step is CEFR. It is in operation from the 2010, and we already finished the construction. And the second steps is the FR17 now it's just in operation, and we hope we can get the first concrete day in the end of this year, and we hope we can put it into operation in 2023. The third is the commercial reactor, is the China commercial fast reactor, based on operation of CFR and the CF600. As you know, CEFR is the first fast reactor in China. Its thermal power is 65 megawatts, and the electrical power is 20 megawatts. It's uranium oxide fuel and sodium cooled pure type fast reactor. In the last year, in 2016, we have, the CFR operated 23 days at nearly 40 megawatt thermal power, never in 2016. So it means that the most time of last year, the CFR is in overhaul. Overhaul include the periodic maintenance, such as the primary and the secondary pump, sodium pump, and the fuel handling machine, and also include some update work. Update work means include the thermal insulation system, especially in the sodium loops rooms, yeah, and also include the digital control system in the main control room, and also we need to make some repair and rectification include the nuclear acid auxiliary system, include the instruments and industrial television system, and also the radiation monitoring system, electrical system repair, and the safety system, and the reactor protection system. So it's really the hard work. Yeah. Also with the support and help from Russian experts. And the FR600 is just in design. We already finished the preliminary design and submit the preliminary safety analysis report to our safety review safety authority agency in China. The FR600 is thermal power is 1,500 megawatts, and the efficiency is 40%. And we also consider use the MOX fuel, and we keep the bleed ratio to be larger than 1.1. So we increase the core damage frequency and the frequency of the larger radioactivity release according to a very high level of our safety authority. Yeah. In this case, we developed the sodium fast reactor, the fuel or the core materials. Focus on the fuel cladding, include the 116 stainless steel, and also the China produced chromium 15 and nickel steel. Also include the ferritic materials steel and the oxide dispersion strengthened steel. Here I will introduce the CN1515. We also have the plan to for e-radiation test for post e-radiation examination, and after that for the application. Here is the picture about the CN1515 cladding and the duct fabricated in the fabricatory. Also, we make the radiation device for these materials. We will put it into the CFR later. About the ODS alloys, we combine some organization to develop it together, include the China Iron Steel Research Institute Group, and also include the Beijing University of Science and Technology, and also include the CIE. We also get some parameters of the ODS. Include the ODS composition design, and we make the density measurements. The processing is the MA and HAP. You can see some pictures about this. Is the precipitates in the field emission, scoping, and time. The second materials is concerning with the equipment structure materials. Some smelting, the processing include the blast furnace, hot material pre-treatment, and converter deep to take off, and include the AOD and the VOD and the left the procedure. We also get the materials gradient design of the ODS, and also we make the analysis of some elements influence on this material. Some curves, the deformation resistance control the 316 and KD and LN stainless steel. Concerning with the rect design, here is the picture show the rect block and in the pool, some thermal flows, 3 thermal flows and the safety analysis results. So the first part is concerning with the fuel cycle. In China, we consider the closed fuel cycle includes the 2 steps. The first step is based on the fast react, the MOX fuel. We use the MOX fuel fast reactor combined with the aqueous reprocessing plants and the high level waste disposal plants. Let's build the closed fuel cycle. We hope we can realize it before 2030. After that, we also consider that develop the method fuel in the future in the commercial fast reactor to get a more higher the blade ratio, and to enlarge the amount of the nuclear plants based on the fast reactor technology. Based on the method fuel, we need the parallel reprocessing plants in the near future, near the 2015. After that, we also consider the mal-actualized cycle, use the fast reactor or ADS, the external-driven subcritical system to make the transmutation, and combine with the reprocessing plant. Yeah. Now mainly we consider the uranium plutonium and the mal-actualized cycle. The 2 steps. First step is based on the CEFR in the laboratory level for the closed nuclear fuel cycle. The CEFR, we built it, and then we used the reprocessing pellet plant. The pellet plant, the pool storage capacity is 550 ton heavy metal, and we also already built the reprocessing and radiochemistry laboratory, include the 9 hot cells and the 5 warm cells and global boxes. So it's a big laboratory for radiochemistry, and we also built the MOX laboratory, include the 5 kilometer 1 year the MOX fuel planet, and the CFR says subassembly, fuel and test subassembly it lined and will put into the CFR is radiation. The second step is the industrial development of the nuclear fuel cycle. in our consideration, in 2030, to realize the middle industrial scale of the closed field cycle, include the fast reactor, the reprocessing plant, and the MOX factory. The MOX factory. Now, from 2008, the significant research project of reprocessing is initiated. And we have the plan to start the MOX plant and the fast reactors. Now it is approved by our government. And also, we select somewhere to build the high level waste treatment plant. So finally, we make the conclusion is the nuclear energy of China will be significantly development with the challenges. The challenges mainly focus on the inland side, and also the economy. As you know, the cheap coal, rapid electricity price decrease of the solar and the wind, high capital cost of the nuclear power plants, and because of the high safety requirements, that's also the challenge. And the second point is in China, several new generation nuclear energy systems are under study to meet the fuel demands. Here include, the sodium fast reactor. Also, we have the plan to build the traveling waiver reactor, include this, and include the lead fast reactor with the accelerated driving system, and also include the molten salt reactor, very high temperature reactor in China. Yeah. When we talk about the sodium fast reactor, we also consider 3 steps. Is the experimental fast reactor is CFR, and the demonstration reactor is FR600, and the commercial fast reactor in the future after 2030. Finally, we say that the closed nuclear fuel cycle is decided from the perspective of the sustainable development of the nuclear energy. That's all. Thank you for your listening. Yeah.
Thank you, Dr. Yu, for your very nice, clear presentation and giving us a picture of nuclear power development in China and especially fast reactor development. And now we have short time for a couple questions from the floor, from audience, please.
Yes, this is Edwin Lyman from the United States. Maybe I missed it, but could you say something about the fuel fabrication for the CFR600? What facility do you have to produce the first core for that with MOX fuel? Thank you.
Thank you. For MOX fuel, we have the schedule. The final decided schedule is in the end of 2018. We will put the pellet, the MOX pellet, the MOX fuel pin into CFR for isolation. And after 2 years isolation, we plan to make the PIE, the post isolation examination in 1 year, and we hope we can get the good results of the MOX field after the evaluation in CFR and get the approval or permission from our safety authorities, and to match the requirements of CFR in operation before 2023.
Thank you,
Yeah.
Dr. Yu. More questions? Over there. It was there. Yeah.
Shigenobu Kubo, JA from Japan. I have a question about your future plan about nuclear power deployment. So, according to your explanation, you expect very huge number of nuclear power around 2015, 50, about 400 or 500 gigawatt. So, I'd like to know about your expectation about fraction, how much fraction of fast reactors at that time.
Sorry?
Fast reactors. Maybe the most part of the nuclear power comes from the PWRs at that time, but how much about it?
Yes, that's a good question. We have the study report from some institution that the result means that the limitation of the amount of PWR, maybe it is be the 200 gigawatts. So if we need to reach the 4 or 5 gigawatts in 2015, so after the 200 PWR, the other parties must be fast reactor. But it's just a study in consideration. It's not the determination of our government.
Okay, thank you.
Thank you.
Yeah, thank you. Thank you. Let's thank Dr. Yu and applaud again. Yeah. Thank you, Dr. Yu, and wish good luck to China in developing all the directions of nuclear power, and we hope you would succeed on it. Thanks. And now our third key speaker from France, Mr. Sylvestre Pivet, with presentation status of the French fast reactor program. Mr. Sylvestre Pivet is the deputy head of the nuclear energy division at the French Atomic Energy Agency, CAA. He is in charge of the R&D programs in support of the nuclear industry and for the preparation of the future of nuclear energy in France. Please, Mr. Pivet, the floor is yours.
Thank you. Is it all right? Thank you, Mr. Chair. You have something to do with it? It's off. Thank you, Mr. Chair. Right. Ladies and gentlemen, dear colleagues, it is my pleasure to present the status of the French fast reactor program. And this presentation has been prepared with my colleagues mentioned on the slide, whom I thank. After an introduction on the current and foreseen French fuel cycle, this talk will be divided in two parts. The first one considering the different topics addressed by the French fast reactor program, and the second one focusing on the sodium-cooled fast reactor program. So let me begin with an introduction on the fuel closed cycle. The spent fuel reprocessing and recycling were implemented in France more than 30 years ago, and processing spent fuel allows to salvage recoverable material, whereas the other compounds are considered as ultimate waste. All the plutonium recovered by reprocessing is recycled in mixed uranium-plutonium oxide fuel, called MOX fuel, whereas fission products and minor actinides are incorporated in glass, then stored pending their final disposal. And this policy has a number of advantages in terms of resource saving, plutonium inventory control, reduced ultimate waste, which does not contain large quantities of plutonium, and safe packaging of this waste. However, multiple plutonium and uranium recycling is not achievable in the current fleet of water reactors. So what about the long term? In order to preserve and to prepare the possibility for the next generation to use nuclear power, uranium resource should be preserved and waste burden should be minimized. The complete closing of plutonium and uranium fuel cycle is an answer to this concern. It implies to perform recurrent and systematic recycling of plutonium and uranium and to operate some reactors able to take the best advantage of these recycled materials within a nuclear fleet. So fast neutron reactors appear as the most suitable and efficient reactors to reach that aim. They efficiently convert uranium into plutonium, and they are able to fission all plutonium isotopes. This appears as the best way to completely use the plutonium and to open the way to a drastic extension of uranium valorization. Among the 6 reactor systems of Generation 4 International Forum, France pays interest to 4 of them. And France carries out research on those 4 systems, of course, at very different level: sodium-cooled fast reactor, very high temperature reactors, considered through material requested by such reactors, and through hydrogen technologies earlier developed by the CEA, also gas-cooled reactor and molten salt reactor. The French Generation 4 program focuses on sodium-cooled fast reactors, considering both the reactor and the fuel cycle. In fact, France has brought a major contribution to the development of those reactors in the past decades. Yet there is a strong connection between the technological maturity of the process and nuclear safety. Technological control associated with significant experience feedback contributes to guaranteeing the safety level of a system. And amongst the 4th generation fast reactor system, only the sodium fast reactor have a sufficient knowledge base in France to meet the technical and operational expectation of a 4th generation system in the medium run. With this in mind, I would like to emphasize again that the French fast reactor program also includes an active survey and some specific studies on other Generation 4 systems through the European projects, through the task of the GIF, and specific cooperation agreements. And I will move forward to the second part of this talk to give you an overview of the ASTRID project and of the development underway at the time being. The name ASTRID expresses the general objectives of the reactor. ASTRID means Advanced Sodium Test Reactor for Industrial Demonstration. It is neither a prototype nor a first of a kind. Its objective is to ensure that a fourth generation reactor type achieves a technical maturity for the second half of this century. And based on the feedback experienced of past sodium-cooled fast reactor, Astrid is designed to demonstrate the relevancy and performances of the technology breakthroughs and of the innovative options at an industrial scale, in particular in the field of safety and operability. The CEA is the leader of the Astrid project. A design core team has been organized through a set of bilateral collaboration agreements, and at the time being, 15 industrial partners have joined the Astrid project. The organization is shown on this slide. The role of the CEA involves the operational management by a project team also in charge of the industrial architecture, the management of most of the R&D work and qualification of technical options, the assessment of studies carried out by our industrial partners in charge of technical work packages, and the direct management of the core work package. So as I said, the CEA has set up bilateral partnerships with key industry partners in France and abroad. The partner provide both technical and financial support. Support to the CEA project owner team is provided by the EDF. The design is organized in engineering batches. Areva NP shares the design of the nuclear island with a consortium of Japanese partner, JAEA, Mitsubishi Heavy Industry, and Mitsubishi Fast Breeder Reactors. General Electric is in charge of the power conversion system. Bouygues carries out studies on innovation for civil engineering. NOx is in charge of the balance of plant, and SEIV of the post-irradiation experiments hot cells. And innovative developments are carried out by several companies such as Toshiba for sodium electromagnetic pumps, Onet Technologies on inspection machines, Technetics on tightness seals, Velan on sodium valves, CNIM on manufacturing processes, and Airbus Safran launchers on reliability methods. So about 600 people currently work on the Astrid project, 60% of which in the partner companies. So such partnerships enable the CEA to concentrate on the Astrid design by implicating key industrial partners whose experience and skills in their fields are very efficient. And such an association of industrial partners offers several advantages, fostering innovation, ensuring that industrial issues are covered as early as the design phase, while providing a source of funding for the conceptual design phases, since the partners partially finance the project. The main industrial cooperation on the Astrid project is a cooperation with Japan. Both Japan and France have developed technologies for sodium fast reactors for several decades. Collaborative R&D arrangements exist for a long time between the two countries. A common will to cooperate on the Astrid project emerged in 2013, leading to a general arrangement signed in May 2014 at government level, followed by an implementing agreement signed by GAEA and Mitsubishi Heavy Industry and its subsidiary Mitsubishi Fast Breeder Reactor, Areva, and the CEA. This shapes the principles and the governments of the R&D and design activities with several task sheets describing the technical program, the deliverable, deadlines, and so on. In the design field, the Japanese team contributes directly to the Astrid basic design on 3 topics: active decay heat removal system, control systems, and seismic isolation system for the reactor building. The R&D field is wide and with a lot of other topics. And after nearly 3 years of common work, it has been shared that collaboration is efficient and fruitful, and so the discussions continue to enlarge the shared scope, in particular in the design field. Since 2007, the CEA has developed a panel of international partnership in order to share, to reinforce, and to spread its R&D efforts. The first framework for those developments has been the European initiatives, among which the European Sustainable Nuclear Industrial Initiative, or ESNI, promoting and facilitating efforts to the different partners. Several European SFR dedicated projects have been launched, including recently the INSPIRE project on MOX fuel licensing. Besides this quite large network, Astrid qualification needs require to widen R&D collaboration. From 2014 on, the CEA set up new bilateral agreements called ARDECO framework, ARDECO for Astrid R&D European Cooperation, standing for, this involves many partners in the UK, in Germany, in Sweden, in Switzerland. Beyond this European R&D network, there are other existing and or possible international cooperation with the Russian Federation on many technical topics and on the use of R&D facilities, with India on safety items and severe accidents, with the US that performed an evaluation of the core characteristic and which R&D facilities might be further used, with Kazakhstan on an experimental program performed in IGR. Several items are discussed with China, and the use of Korean R&D platform is also under discussion. Now let's see the Astrid project in itself. In December 2015, the Astrid project met a milestone of the end of the conceptual design, and the CEA delivered 2 synthesis files to the French government and got the authorization to proceed to the basic design phase until the end of 2019. The reactor itself has the main technical options as shown. I won't comment them because presentation in parallel sessions will go through the details of it. 2 options are considered for the power conversion system. During the conceptual design phase, the reference configuration was a steam-water power conversion system. This mature option benefits from a large experience and tens of unique operating years. Steam generator design improvement allows to reduce the risk of sodium-water reaction occurrence and to mitigate its consequences in case of a hypothetic violent reaction. Another way of dealing with this reaction is to avoid water in the power conversion system, and that is why the second option of power conversion system is considered. In this very innovative option, the water-sodium reaction risk is inherently eliminated by replacing water by an inert gas. No showstopper has been identified so far. So the direction remains to increase the maturity level of the gas PCS configuration while keeping the 2 options open, gas PCS or water steam PCS. The general layout is shown on this slide with the reference site for the design. The reactor and the safety buildings are located on the rock. Nevertheless, main buildings are designed to lay on seismic isolation. In addition to the available experimental platforms in other countries, the French fast reactor programs includes investment in R&D facilities with the refurbishment of the Mazurka critical mock-up, the new Cheops hall for large-scale sodium loop, the Plinius 2 facility for severe accidents and corium behavior R&D. And of course, the existing platforms are used to carry out experimental validation of new concepts. An example of experimental concept validation is shown on this slide, illustrating the development of ultrasonic techniques for under-sodium vision. The target is a mock-up that can be seen on the left with different shapes, including small slits. With new sensors and new post-treatment code, it has been possible to scan the mock-up submerged under sodium with satisfying accuracy, considering the fact that the smallest slit is only 0.5 millimeter thick. And this slide illustrates the R&D on fuel and core materials. Regarding SFR MOX fuel, 2 succeeding campaigns of pellets production have been launched in the Melox facility with the expected quality of microstructure. In addition to that, tubes of cladding have been manufactured by 2 companies with satisfying results. Wrap wire winding has been successfully tested by the CEA. So this example illustrates the endeavor to reshape the industrial capacity to produce SFR fuel assemblies. And the picture down on the left illustrates the post-irradiation examination on fuel cladding tested earlier in Phoenix reactor with the Astrid reference steel cladding. The same kind of post-irradiation examination are carried out on irradiated fuel pellets. And finally, an assessment has been made on additive manufacturing capabilities for complex shaped pieces of the fuel assemblies, such as can be seen on the right. So to wrap up and conclude this presentation, I emphasize that since nuclear energy is a well-proven source of large baseload electricity with no greenhouse gas emission, it will remain one of the pillars of the low-carbon energy mix in France. The closed fuel cycle associated with fast neutron reactor will lead to drastic improvements in uranium resources management and important reduction in footprint and radiotoxicity of final wastes. In this context, the French program on Generation 4 systems is based on the Astrid program on one hand and on active survey on other Generation 4 fast and thermal neutron systems on the other hand. The basic design phase of the Astrid project is ongoing until 2019. Schedule and organization for the next phase are under preparation with the French government in the framework of the French-Japanese partnership and with our industrial partners. Thank you for your attention.
Thank you. Thank you, Mr. Pevet, for your nice overview of the fast reactor research and development in France. And some questions from the audience. Yes, please. Leonid. Where's the microphone?
Thank you, Mr. Pivet, for your presentation. Have you any expectation when the first Astrid reactor will be built?
As you noticed, I have not presented any schedule. We have a clear program, as I said, until the end of 2019. This is for the basic design phase. Afterwards, things are under discussion. And also, as we know, we have a new government after the election of the new French president, Mr. Emmanuel Macron. So we have to have high-level discussion on the French nuclear policy, and Astrid is a key element of that. So Astrid has a strong support by the French government, and for the future, the discussion have to take place in order to have those discussions, including on the schedule.
Okay. One more question. Two questions, yeah.
Yes, thank you. Ed Lyman from the United States. I wonder if you could comment on your decision to go forward with oxide fuel for the reactor. You heard from the other panelists this morning that perhaps nitride had safety advantages, or metal fuel from the Chinese participants. So could you describe the basic thinking behind going forward with oxide? Thank you.
Well, I'm sorry, because we have the sound is echoing there, so it's very difficult to hear your question. The question is about fuel.
Should I repeat the question?
So I understand that the question is about the fuel, MOX fuel, and
yes, the choice of oxide for Astrid. You've made a final decision, but other panelists have talked about other fuel choices that they say have advantages, for instance, nitride or metal. So if you could comment on the decision behind oxide.
All right, thank you. Well, the reference fuel for Astrid is MOX fuel. So what is planned is that Astrid should begin with uranium and MOX fuel, and the expectation is to test as soon as possible recycled MOX fuel, fuel manufactured with recycled MOX fuel from the current fleet from the French current nuclear fleet.
Okay, thank you very much, Mr. Pivet, and let's thank and applaud again, and thanks. And unfortunately, we are a little bit behind of scheduling already, and we had opportunity to listen three main countries who are hard working in fast reactor technologies, and let's wish them successful continuation of their research and development, and successful putting in operation their prototypes and new fast reactors. On this, I would like to conclude the first plenary session #1. Thanks again, and let's applaud.